Bueno, muchas gracias por su participación. El día de hoy vamos a estar hablando eh, sobre infraestructura e instrumentación sísmica, en donde Nicolás va a partir presentando un poco lo que hacemos y después vamos a dar espacio a Carmine, quien es especialista y doctor en PCB pisotrónica. ¿Ya? Vamos, Nico.
Bueno, hola a todos, gracias por unirse a este webinar. Agradezco ahí la organización de Carmine y la organización de Benjamín. Y bueno, hoy día vamos a hablar un poco de sensores para instrumentación, o sea, instrumentación sísmica para infraestructura, sensores de alta sensibilidad. Voy a partir presentando un poco lo que somos nosotros como Varitec. Qué hacemos y cómo nos relacionamos con PCB Pisotronics. Somos una empresa que se enfoca en soluciones de tecnología predictiva, originalmente enfocados en la parte de máquinas rotativas, análisis de vibraciones en motores y en máquinas, ¿cómo se llama esto? En análisis estructural y principalmente en máquinas rotativas. Esta empresa nació en el 98 con el foco de dar soluciones en el área de mantenimiento predictiva y a partir del año 2000 trabajamos con Rockwell, IRD, y Entec y IRD en soluciones de monitoreo predictivo. A partir del 2008 empezamos a trabajar con PC Pisotronics, ya van más de 10 años. A lo largo de esto hemos trabajado tanto en el área asociada a monitoreo de condiciones en el área industrial, así como en el área de instrumentación estructural y en el área también asociada a sensores utilizados para investigación y desarrollo en el área más académica. Actualmente somos integradores de Rockwell Automation, enfocados en el área de monitoreo de condiciones y además somos distribuidores de PCB Pisotronics y todas sus divisiones. Trabajamos con Divisoft como sistema de adquisición y también trabajamos con Sensotec EIR de balance. Estamos aquí ubicados en Santiago y también en Calama. Y bueno, llevamos a lo largo de 26 años entregando soluciones predictivas, sistemas llave en mano y suministro de equipos a distintos tipos de empresas. Nuestras áreas tecnológicas, bueno, PCB Pisotronics es una empresa compuesta de varias entidades. PCB Pisotronics está dedicada al área de investigación y desarrollo y van a estar principalmente los sensores sísmicos de los cuales vamos a discutir hoy día. En DEPCO, que es un área dedicada a instrumentación MEMS, instrumentación de presión dinámica, y también algunos sensores para turbinas y instrumentación para turbinas. Y de Model Shop, que apalanca un poco a PC Pisotronics en el área de calibración y de sistemas para garantizar que los equipos fabricados por PC en DEPCO y en realidad otros clientes tengan las mayores atributos, o sea, las mayores, ¿cómo se llama esto? Las incertidumbres más bajas en sus sistemas de calibración. Model Shop es uno de los líderes actuales en sistemas de calibración portátil y de estaciones de calibración. Y en realidad creo que es una de las partes que le da más potencia a PC Pisotronics con respecto a calibraciones, ya sea a alta frecuencia, desde, no sé, digamos, 100 Hz hasta 10 kHz, a calibraciones hasta 0,1 Hz. Cuando vamos a ver que tenemos sensores que llegan a frecuencias muy bajas, Model Shop, con sus sistemas de calibración, garantiza que los sensores que entregamos van a poder cumplir a frecuencias muy bajas. Y bueno, Divisoft, que es la parte que igual puede ser integrada en nuestros equipos, que son sistemas de adquisición de propósito general, tanto máquinas rotativas como infraestructura. Sensotec también y IRD apalancan un poco el área industrial junto a Rockwell. Aquí se ve un poco lo que mencionaba anteriormente, calibración como el área de Model Shop y bueno, investigación y desarrollo, donde tenemos a Pisotronics y Enderco. Y como empresa, bueno, nos enfocamos en sistemas de monitoreo de condiciones, sistemas de monitoreo estructural, calibración de sensores, montaje de sistemas para proyectos llave en mano, ingeniería de confiabilidad y, bueno, darle todo el seguimiento de lo que significa un sistema de medición, ya sea sísmico o industrial en el área de monitoreo de condiciones. Eso es como una versión súper abreviada de las cosas que hacemos. entregamos servicios y entregamos también suministros y hacemos ahí apoyo en integración de distintas soluciones y proyectos. Y aprovechamos de apoyarnos harto en las áreas que tal vez son más incipientes, por ejemplo, en Chile. Aprovechamos justamente el apoyo aquí de Carmine y de fábrica de PC Tronics en asesorías técnicas con respecto a recomendaciones a ustedes, los clientes, y recomendaciones a nosotros en caso de cualquier como incertidumbre. Ahí se agradece mucho el tener un enlace directo a, bueno, Carmine y gente en fábrica con mucha experiencia en un amplio rango de aplicaciones, en este caso que vamos a ver de infraestructura y sísmica. Dicho esto, voy a darle la palabra y, bueno, introducir ahora a Carmine, que va a dictar la parte de webinar. Esto va a ser en inglés, vamos a tener la opción ahí de cualquier pregunta, puede ser en inglés, vamos a traducir, y Carmine también no da ningún problema con alguna pregunta en español. Eso, y bueno, démosle inicio ahora a la parte ya más técnica. Y bueno, aprovecho de nuevo agradecer de nuevo su participación. Carmine, te dejo
Yes,
ahí.
okay. I'm here. Nicolás, buenos días a todos.
Buenos
Muchas
días.
gracias. Fortunately, I don't speak Spanish, but maybe I can understand something. Okay, let me share my screen. Now, can you see now?
Perfect. Yes.
Okay, good. So, anytime there's any problem with audio, video, Nicholas, please let me know. And at the end, we have a question and answer session. So feel free to ask your preguntas in English or in Spanish. Okay, today agenda is we have a 6 point, but I would say practically is 0.5. 0.5 because we will see 26 different cases, different applications. Most of them are covered by papers where we can see how we can use our sensor, different sensor for infrastructure test or monitoring. So after this brief introduction, we'll see a little bit of our PCB accelerometers and other sensor. And then we go to the Triaxial seismic accelerometer, the new one, which is just released at PCB. Then we will have 0.4 and a very, very quick overview of few of the two of the most common other sensor used in this kind of vibration test and monitoring in the market. And then, as I said, we will see 26 case studies. So it's quite long because of this 26 case study today. Okay, so the first part is obvious. Why we do these measurements in infrastructure. There are many kind of reason why. First, for test infrastructure, or for maybe to perform a monitoring. You can imagine on some monuments, or for, I guess, seismic, or maybe for certification, or even simply for research scope. So there are many reasons. I would say very important reason. The question is which kind of system we use for measurement. We use typically sensor with a cable and data acquisition. Of course, I will concentrate on type of sensor because the sensor is the one that transforms the electrical output in the oscillation in an electrical output, which can be read easily by any data acquisition. I hope it's enough, or should I speak slow, Nicholas?
I
Should I
think
speak
it's
slower?
maybe
okay?
a bit slow.
A little slow, okay. Okay, that's a curiosity. You can find in one of our paper on our website. We talk about more than 3,000 years ago, 2,000 years ago, where in the China dynasty, they attempt to make the first, I would say, sensor to monitoring or vibration or seismic or whatever. It's a very easy, you can see a pendulum here. I hope you can see my mouse, where this ball, due to this movement, we drop to the frog mouth. Why this drop? Of course, when you have a movement, and this movement is due to some vibration from the soil, from the ground, especially use it to monitoring eventual eventually an earthquake from distance. Well, one day, one guy from the court found the ball dropped in the mouth of the frog. But was very strange because they didn't feel anything in the kingdom. No movement, no seismic, nothing, no earthquake. So they believe probably was a false alarm. Well, after a few days, in the time where the guy moved by horse from one city to another city, arrived and announced there was a few days before an earthquake, exactly the time when the ball drops. So as you can see, this is just a curiosity where the first, let's call, sensor was developed. Of course, today we have a different type of modern technology. I will concentrate on a couple of technology only. First of all, the piezoelectric one, which I hope are familiar for most of you. We have the silicon dioxide, mainly due to quartz or another ceramic piezoelectric material, which generate when we have a force acting on it, like an acceleration, generate an electrical output. This electrical output is our impedance. So typically we have a MOSFET, a microcircuit inside the accelerometer to convert to low impedance voltage output. And this is one of the most common. We have another technology which is capacitive, we'll see later. The piezoelectric is especially for this infrastructure where we don't have associated high temperature above 120 degrees Celsius. Then in this case, an ICP sensor with the electronic inside and low impedance output, voltage output, is very, very common. Most of the piezoelectric sensors, which are very robust, can measure in any type of infrastructure with a very low level, which means they can reach very high sensitivity to measure down to, let's say, micro G. The PCB sensors are very different. As you can see, I'm trying to be quick on this part because I would like to show you the 26 different cases. So you can see they are very different. So how you can recognize this one from this one? I would say these are mostly all piezoelectric sensor, accelerometer. But this is a triaxial for seismic, new one, triaxial high temperature. This triaxial high sensitivity, miniature sensor, not high sensitivity. So of course I know all this, but it's not easy to select the proper sensor. So I would say, which are the requirements? Where we are? Well, if we want to depict in a plot diagram with the magnitude level G and the frequencies, the frequency on x-axis, you will see the seismic range or infrastructure range, please follow my mouse, is in this region where we can measure very low level of G and very low frequency. As you can see from the level I took from website, most of the infrastructure measurement like earthquake, local damage, traffic detection, most of these are above micro G. What does it mean? If you have an accelerometer which is able to measure down to micro G, is already good for most of our needs. Maybe not nuclear tests, but all the rest are fine. Then I found another interesting plot, another interesting information here on the right side, bottom, because these are the acceleration level for which the building in a seismic area in Italy, for instance, need to resist according to law. So as you can see, the minimum 0.05 G. So in this case, there's no need for seismic monitoring and test in these seismic areas to measure below 0.05 G. So even not micro G. These are very important information, at least for the level of a vibration to measure. Because look at this. If you want to design to make a list of requirements, of course, we know that maximum 100 Hertz and the G range is for sure not below micro G. The frequency, I already mentioned, maximum few hundred Hertz, but the question is, do we want the really 0 Hertz or we want very close to 0 Hertz, but not close to 0 Hertz? Remember, we are measuring motion. We are measuring a structure, can be a big building, can be a bridge, can be anything which is big, is moving. When you are going to move, you have a frequency even very close to 0 hertz, but you don't have 0 hertz. And therefore, most of the application we can cover with not the capacitive sensor technology we have, but with the piezoelectric ICP. Another important thing is robustness. You can imagine an hermetic sensor, if not hermetic, exposed during monitoring. Then the robustness is also important for shock, because if you drop on the floor an high sensitivity accelerometer, you can break it. The size is not so important. The price, of course, depends on the number of channels we need, if it's a test or if it's a monitoring. And then, of course, the ability to use long cable. Because today, we have some technology wireless, but not for civil infrastructure, because remember, we measure very low frequencies. Therefore, long cables. But long cable, we don't have a problem with the ICP because it's amplified already. So the piezoelectric technology, as you can see, this red area. However, the light green is starting from 0 hertz. The light green is capacitive technology MEMS, micro electromechanical system sensor made by silicon, and I will show you some of them, some example. Now, why I call micro vibration? Because as the accelerometer with the high sensitivity. High sensitivity, we talk about from 1 volt to 10 volt G, enabled to measure up to down to micro G. Here, these examples are all piezoelectric accelerometer with the 1 and 10 volt G, most of them single axis. But now we have the new one, this one, which is the first triaxial ICP accelerometer with 10 volt per G. So we can measure down to 8 micro G. The same, but triaxial, but capacitive, but not able to measure down to micro G, but milli G, is this MEMS. The ability of this sensor is to measure from 0 hertz because it's silicon made. As you can see, most of the application here of this sensor I show you are for many applications in the civil structure. Can be traffic jam or dams or buildings or infrastructure like I don't know, viaduct or tsunami or railroad. We have many application infrastructure. And of course, these are the primarily standard off-the-shelf accelerometer single axis. You can see typically in 1 volt G, 10 volt G. You can see the frequency, 0.06 hertz. So really close to 0 hertz. You can measure down to, I would say, every type of motion. Of course, when it's at 0 hertz displacement, you cannot able to measure. Otherwise, you are able to measure down to micro G level. Okay. And this is a brand new. I would say this development that was released this year is a triaxial accelerometer. You can see the size. The size is very small compared to, instead to use a 3 accelerometer to the same size, which you can see. This could be using these 3 axes instead of this one. That's why it's very convenient to use this accelerometer. You can see the size. And the level is 8 micro G, already mentioned. So you can measure from 8 micro G, you can see the frequency, even 0.06 hertz, which means most of the motion in the infrastructure, you can measure in the 3 axis. This is really the new that we have today. I am pleased to present because probably the first time I'm presenting a webinar officially, I would say released today in a small number of pieces. In the future where the production will go ahead, we have a large quantity available. And as every other sensor is important, is coming out with a certificate of calibration. Nicholas already mentioned about calibration. Yeah, this is very important because otherwise you don't know if the sensitivity is valid at all frequency, and if the reliable and the quality of the sensor that you use to measure. However, we have the opposite. We have some very small sensor, very low price, eventually to build, I would say 1 volt per G, this sensor here, this accelerometer, naked. Just the accelerometer itself need to be protected in a case. But the price is very low because this can be embeddable in any application. Of course, this is primarily for monitoring, not for testing. But sometimes when you want to have rough results, but large quantity, then you can use this one. And I promised to you, right, the DC, just to have a look of the technology capacity, because we have two plates, and then where you mounted the gauges, and then the sensor is moving up and down and develop an output. This output, you can see the sensitivity. When you have 600 millivolt per G, you can measure up to 2G. But unfortunately, you can measure down to 0.1 milli-G. So the good things of this type of solution, accelerometer, we have different types, even Triaxial, is the ability from 0 hertz exactly. Therefore, if you want to have the displacement, a very, very low frequency, eventually you can evaluate this one. And this is one of the latest news, the Triaxial, which can work single-handed or differential. We don't have time to explain the difference, but is an accelerometer you can see measuring from 0 hertz, just to explain. And this is 60 micro G, the resolution, so the minimum level. However, the Triaxial piezoelectric is 8 micro G, so one order of magnitude of difference. Of course, I will not mention force sensor and other sensor like the strain sensor, because these sometimes are part of this 26 different cases I will going to show. Now, before to go to the 26 different cases, let me show you the two typical ends, two typical sensor. The low end typically use a geophone. You know, every geologist probably use this geophone, which is really rough. The cost is very low, but is very limited in frequency. Any frequency they can measure. It just gives an idea. Our sensor, I showed you before, the embeddable one, has a better characteristic and probably the same price level, not exactly the same price. So eventually you can evaluate the embeddable. However, the high end, this kinematric, is excellent sensor because you measure from DC to 2000 G and it's Triaxial and measure down to nano G. My point is, nano G isn't really needed for your measurement, or is enough micro G. First point. Second point, is fragile because if this sensor drop on the floor, you can easily break. However, our sensor like this one is very robust, can resist to 1000 G shock. Okay, that's the difference between these two typical sensors using in infrastructure. Okay, I hope there is no urgent question, because now we go to the last and the longest part of this presentation today. Nicolas and Nico, any comment?
Por ahora no. Igual quería comentar respecto del acelerómetro triaxial, lo que dijo Carmina, que este es un sensor que salió recientemente este año al mercado, y diferenciarlo un poco de algunos otros sensores sísmicos. Es un sensor que es bastante robusto, puede soportar 1500 G de choque, además de poder medir, o sea, además de su rango de 0,5, por lo tanto, es un sensor que es bastante más robusto que algunos otros modelos que nosotros mismos trabajamos y que tienen un rango ahí de choque un poco más, bastante más bajo. Pensando en modelos como el 393, B31, este sensor es mucho más robusto. Y bueno, esperamos este próximo año empezar a traerlo y empezar a facilitar un poco los requerimientos que nos han llegado con respecto a, oye, tengo estos 3 sensores sísmicos, necesito montarlos. Siempre hay bueno, hay más versatilidad, pero también hay más posibilidades de error. Este sensor, el 354A12, viene a facilitar esas mediciones. Eso más. Carmine, continuemos con aplicaciones.
Okay, now we see the application. Yes, many applications. The first one, obviously, is a test in infrastructure in a typical lab, right? Can be a testing lab, or can be the lab in a university, right? Can be easily. In this case, of course, what you need a typical high sensitivity accelerometer, but also with a force sensor, a sensor that is able to measure with the same ICP technology the force, the dynamic force. Because of course, the modal test, you need to excite the structure, can be a sledgehammer, can be any device, and then measuring the force you give, and then the accelerometer to measure. And these you can imagine a pump or any structure. You can see the hammer, sledgehammer to excite the structure, and the accelerometer, not needed to be a 10 or 1 volt G, it can be even 100 millivolt per G to measure the response. And of course, we have plenty of these sensors. These are very general introduction because excitation method can be hammer or shaker. All these sensors are manufactured by PCB Group. You can see the shaker is the best, I would say, excitation in the model test, and then different type of hammers. There is another application. This is a real application made in Belgium on oil platform. On this oil platform, you can imagine how much is important to measure the vibration for safety, right? Or security over this platform. In this case, the University of Brussels used a 393B04, which is a ICP 10 volt per G, and the capacity MEMS 2G range, in order to measure every displacement, deflection, and vibration inside this platform. You can see we have a 6 level of platform with this 13 location, and we use they use 16 accelerometer, this one. So that, I'm sorry, I will be very quick on each application because 26 are a lot. These are real application. Another real application are very common because this consultant in Germany, they use a 43 accelerometer for monitoring, permanent monitoring on during consultation of I would say building preservation and monument conservation project. As you can see, these are very common application in any country, not only the seismic country, but every country that want to preserve the monuments. This is in the US now. This is the building, the most equipped building, monitoring building in the world. Is covered by a paper. You can see the link of the paper. When I will send the presentation to Nicholas, he will send to you. So please make sure that you send your email address to Nicholas and Benjamin, and they will send you this presentation, okay? So in this presentation, you will see the link, and you can download the paper. And you will see that they use 212 of 393B04 from PCB 10 volt G for permanent monitoring of all these structure, which is a big structure of the Virginia Tech. So very big. You can imagine the under 60,000 square foot of Goodwin Hall. So very big structure, permanent monitoring. From this building, we go to another building in Italy this time. I don't know if you remember 20 years ago, something like that. There was a big earthquake in the middle of Italy, and the student house collapsed. And then there was a new building for student house. You can see the pillars. On 2 pillars, we decide to embed 2 of 393B12 10 volt G, very robust with milk connector in a box, in a pillar. This pillar was injected by liquid cement, right, in the pillar, and then solidify and still there, measuring the level. This is a paper you can find on our website, which I contributed, of course. And because I followed the project of these 2 units of accelerometer to measure 2 axes in this pillar, in each pillar, 2 pillar. And still today, after 15, 20 years, is still working. Still in Italy, we have in Piedmont region the biggest elliptical dome in the world. So you can imagine how much is important to measure this elliptical dome. Well, this consultant used our 12 or 393B12. Yes, it's very popular. And you can see the picture of these 2 sensors mounted on the facade of the dome for permanent monitoring of the vibration of this very, very important monument in Italy. But another very popular, probably most famous document is the church main cathedral in Milan. You can see the status of the Mother Mary need to be monitoring. We have this accelerometer 393B12, again, this one, used by the consultant engineering to measure in a different level of the column, including the Mother Mary, to permanent monitoring of this I would say this tip of the church. Still in Milan, but this time the stadium, football stadium, but they use the 393B12 not to monitoring during football match, but during a U2 concert, rock band concert. During concert, you can imagine how many people jump, and they use this accelerometer to measure, to monitoring during the event, to make sure that the structure will be not overstretched. Now back to US. US, this is a bridge, and these are kind of robot using a typical 352 C67 accelerometer, which is not a particular one, it's 10 millivolt per G, it's not such a low level, just because this robot is moving up and down around the bridges to assess any bridges. So moving around, he can measure the vibration, and from the response, he's able to measure the response of the bridges and this automatically detect the status of the bridge. Still in US, but this time for roads assessment, using not the accelerometer only, but also a pressure sensor 106 type of PCB inside the tire. Because of course, the tire changed the pressure due to vibration when moving on the road. So with a different pressure, dynamic pressure measured, you will have a different status condition on the road, and then you can build the status of the road with a different color, of course. That's another very interesting application from one of our customers in US. Now we go to China, and this University of Rome prepared a monitoring box with this pellet I showed you before, the very cheap accelerometer in a box with the Wi-Fi transmission, so it can measure the monitoring, not this building, but another bridge in China, and send by the phone the results to University of Rome professor. Still in Italy, but this time on a bridge. This is a paper you can Google in and find, as I did it, because I was not aware. I just simply Google in, I found that this building, bridge is very big. It's very big in the motorway, in a very big, the biggest motorway in Italy. Using 393B12 was funded the modes of the sensor. And this is very interesting because this large bridge, the minimum frequency is 0.93 hertz. Well, I would say this probably is the best proof of what I said at the beginning. So even a large bridge like this one, the minimum frequency is 0.93 hertz, which means that usually you don't need a DC accelerometer, right? We have it, the DC accelerometer, but in this case, the minimum frequency 0.93 hertz can be easily monitored and perfectly measured by this 393B12, which is a dynamic ICP accelerometer, starting from 0.15 hertz. Of course, I try to be quick now, spend few words per each slide, because then I will wait for your questions. That's an interesting application covered by a paper on Sound and Vibration magazine in many years ago. This gentleman here used our strain gauge. Is the only, you can see the foil strain gauge here. You can see my mouse. This is a foil strain gauge, ICP strain gauge comparison with the foil strain gauge is the only reusable strain gauge in the world. So not only the foil strain gauge in this construction work with all this dust was impossible to mount the foil strain gauge on two-pillar metal flange, right? Because too much dusty condition. However, this sensor is hermetic. I would say not hermetic, but epoxy sealed. Inside you have a quartz plate. So mounting on two flange or opposite flange of each pillar, they assessed the status of the pillar during construction work. And this is the results. One column on the left, this one is a column. You can see the time, and this is a time history in zoom. And you can see the two sensors, red and blue, have the same frequency and the same level. Therefore, this is a clearly axial loading of this pillar. Another pillar with the two opposite strain gauges on two opposite flanges. You can see from the zoom, you have the same phase but different amplitude. What does it mean? It means that this pillar, however, has an axial and bending loading. So very interesting application of this strain gauge. Now we go back to Italy. In this case is a Florence football stadium with a famous column. Is a tower. This tower need to be, I would say, tested after some repair around the stadium. And they use a 393B31 high sensitivity accelerometer, of course, with a radar, interferometric radar, to measure the displacement during, I would say, construction. You can see that was very useful, this application, to check the status of the marathon tower in the Florence stadium, football stadium. Now we go to Poland. This is a Labado dance. This is a motorway race, and old people dance in a Labado dance, which means they hold the arm or the arms on each shoulder. So in this way, they are jumping all in the same time. So you can imagine hundreds of people jumping at the same time, how much can be dangerous to excite the resonance of the structure. And in fact, they use a 356B18, which is only 1 volt G, not 10 volt G, because of course you don't need to measure down to micro G, but milli G is enough, because it's a really some G during this Labado dance, right? So the people jumping, it was important to use many of these 356B18 during the event in order to control that no problem happened during the race. Now in US, there was another example. This is a dam. The dam was important because there was in the area of salmonids fishing, moving. So the salmonids during construction, I would say maintenance of this dam, of course, the excessive vibration could disturb the salmonid navigation, right? So there was the triaxial arrangement, 3 accelerometer single exit 393A03. They use it here in the point. You can see the red star in order to, when they're doing construction, the level of vibration is too high. They can stop construction working in order to allow the salmonid to not be disturbed during their navigation, because of course they want to make sure that the salmonid can navigate and create eggs and grow up to be eaten, right? Will affect the production of semiconductor. So we use the three we immediately realized that was some earthquake by distance. And in fact, that was the big earthquake in Japan will happen during this operation. So the Taiwan was the first one to realize something happened in Japan, some earthquake, because they monitoring this earthquake at very long distance. So it's an excellent, I would say, multi-application case, because with the same sensor we monitoring the railway traffic, the car traffic, and an earthquake in order to prevent any problem with a semiconductor industry manufacturing. So it is an interesting application and covered by one of my paper on website. Go back to the university in Tennessee in US. They use a 112 accelerometer. This case, this accelerometer is 1 volt per G, and they use this large number to monitoring for two reasons. The structural air monitoring, and the other reason is to make human vibration I would say, the steps or the people, hundreds of students in the university moving around, and of course cause vibration. And they want to measure also this one. They use this two sensor, strange, one ICP and one charge output from Endeavco. These are the system they use for this permanent monitoring of the Tennessee University engineering faculty. As a general, this is not a case. This is a general suggestion for wind tunnel or models like bridges. We can use a pressure sensor or microphone to measure on the models, because these are very small pressure sensor, to measure the pressure on acting on the model or bridge. You can imagine to evaluate in a wind tunnel the behavior of this structure or model on the wind. However, the microphone was another interesting paper from China. They used two microphones from PCB with a very low frequency measurement, 0.13 hertz, almost below any other accelerometer. And they use this accelerometer to monitoring for structural health monitoring on some infrastructure. So this is very interesting paper, which I found on Google. So please do yourself, and you will find an interesting application using not the accelerometer, but these unique low frequency microphones. But these low frequency microphone, you can see here from PCB, since they can measure down to 0.1 hertz, they can be used for many other applications by non-contact measurement. For instance, tornado, typically in US, or wind farm noise, this is everywhere, volcano, earning, right? Of course, nuclear, because all these events are very low frequency, much below the human ear. So having this type of microphones, they can easily be measured. On railway is a different one. We don't need the micro G. This case can be some level of G's during passage of the train. And then in this case, you can use any typical accelerometer, ICP or MEMS, for measuring not only the vibration, but also the pressure to measure during the tunnel entry of the train, high-speed train. There are many other tests. These are a few examples, but I don't want to go through each details, because otherwise we have no time for questions. Therefore, also do not forget the MEMS accelerometer are typically used for MEMS traffic on the car to measure the event in the car. But also we can have a simple device. We don't want to use against the dual soft, of course, because these are simple one channel, two channel, simple measurement for this Digidac, which is a device which convert and not only power ICP, but also convert data to be measured in a smartphone. It's a very simple device for general survey. The last, of course, since we are in Chile, I would like to suggest which type of sensor can be used in mining to measure during a operation, during a blast, right? Well, first of all, we can use a pencil probe by PCB to measure the air-free field blast, but also by this, and we can use high-level microphone up to 180 dB. For the people, for the miners, you can use the vibration meter, but also dose meter to measure the level of noise in the ear. Also remember that as a microphone, we have the only explosion-proof microphone in the world. So this microphone can measure even underground to see any problem, right? Because in case of any explosion area, it can easily measure without any problem. And finally, of course, the infrastructure close to mining during a mining operation. This triaxial is excellent for this purpose. For instance, a building close to mining. Okay, that's the last slide where I can show you. You can see the papers available on our website. So you can see, you can download this paper free of charge. And also I recommend you to go to Google to download any other paper I show you. Muchas gracias, and I'm ready for your questions.